Hello everyone, welcome to a new math video I'm putting together on my channel. Today I'm going to be going over topics, the Euler identity, double angle, and sum of arguments, trig identities, and yeah, that'll be all. The second video in this series the second video after this will build off of this video, and it will be using these trig identities to prove a trigonometric relation. But yeah, sweet. So let's begin. What's Euler's identity? So Euler's identity is a fundamental relationship of the exponential e term you might have seen in your algebra classes. And it involves complex numbers and Taylor series or series expansions. We won't be covering the math behind those here, but it just so happens that the exponential function has a very interesting relationship with cosine and sine, where if we take e raised to the power of this imaginary number j theta, we have an equivalency, or we equal the following quantity: cosine theta plus j sine theta. And so what this beautiful relationship does allows us to relate an exponential term to trigonometric terms. And why that's really important is because exponential terms are very important for modeling many different things, as well as cosine and sine in natural phenomena in our world. And so when we can relate the two things, we provide the mathematical basis for so many important topics in our world, such as signal processing, finance, things like this. So this is Euler's identity. Some certain things that you can really quick already notice about this identity is you can do two things. So if you know about sine theta, cosine theta, sine of negative theta equals minus sine theta, which means sine is an odd function. Sine is odd. Cosine of theta, negative theta, equals cosine of theta. Cosine is even. So if you want to calculate what cosine and sine is in terms of the complex exponential, like you want to flip this around, take e to the minus j theta, and you get cosine of minus theta. We'll do parentheses plus j sine minus theta, which is going to be equivalent to, what's this going to be equivalent to? Cosine of theta. And then minus j sine of theta. And so with these two terms, you can actually just do some algebra to calculate for cosine and sine in terms of, so adding these two terms together, you're going to see that the negatives on the sines are going to cancel, and you're going to get 2 cosine of theta. So what this is going to be is, if you add these together, 2 cosine of theta is equal to the ej theta plus e to the minus j theta. And then you can just isolate cosine. So cosine of theta equals 1/2 e to the j theta plus e to the minus j theta. Awesome. So how would we do that for sine now? So you'd actually subtract this term from this term. So that will cancel these positive cosines, and then you'll get the following. So if you do e to the j theta minus e to the minus j theta, the positive real cosine terms are going to cancel, and you'll get 2j sine of theta. And then to calculate sine of theta, you just have sine of theta equals 1 over 2j e to the j theta minus e to the minus j theta. So with that basis in mind, that's a little bit of background on complex, this Euler identity idea and why it's so important, and how you can derive sine of theta and cosine of theta in terms of this complex relation, as well as just understanding what that relationship is to begin with. Awesome. So now we're going to take you through a quick, or I'm going to take you, it's not we here, sorry, it's just Sam, just me, going to take you through a quick trigonometric proof for the following identities. So let's say you have cosine x plus y, or sine x plus y. And then notice on this term, whenever you let x equal y, you're going to have cosine 2x, which is called the double angle. And then, because it's double the argument, and then sine 2x. So with that in mind, I'm going to take you really quick how you can derive these. So let's say e to the j x e to the j y. This is these complex multiplied together. This is the same as e to the j x plus y, which is going to equal cosine x plus y plus j sine x plus y. Okay, and now if we want to expand these out, we have cosine x plus j sine x, and then cosine y plus j sine y. And we're equaling these to do the proof. Because in a lot of complex like proof, you just want to show that this imaginary term is equal to the real term. So when you factor this out, we do this thing called FOIL. Whenever you're factoring, you're just doing something called FOIL. So you take the first term, so this is the f, and then you take the outside term, and then the inside, and then the last. And so what we get there, we get cosine x, cosine y, and then what else do we get? We get the minus the real term, the other real term, which is going to be this j squared, because j squared is just -1. So we're going to get minus sine x sine y and then we're going to get plus our imaginary term, which is going to be plus sine x cosine y plus cosine x sine y. And notice this is still equivalent to this up here. So you take this guy, I'm going to put a box around him, and then this guy, and they're equivalent. And then we'll try to do a circle on this guy, and then a circle on this guy. And notice when you let, so we get, so what we were trying to prove here was 1, 2, 3, and 4, right? We were doing the sum of arguments and the double angles. And so 1, what are we going to get? Cosine x plus y, right? So what do we get? Cosine x plus y is just equal to this real term equivalency. Cosine x cosine y minus sine x sine y. What about 2? What's 2? 2 is our sine, or our complex identity. So we get sine x plus y, which equals sine x cosine y plus cosine x sine y. Now notice these once you have these, great, because those are the generalized forms. Then you just plug in x equals y. So when you plug in x equals y, this simplifies. They should simplify. The double angle formulas are more simple than the sum of arguments. So once you do this, you get the following. You're just going to get two terms which are the same. So you get sine x cosine x plus cosine x sine x. And those are the same. So you get 2 cosine x sine x. And what about the other one? Can you try to do the other one? I hope you got it. And if you didn't, pause it and try to get it. So it's going to be cosine x cosine y sine x sine y. When we plug in y for x, we get the double angle for cosine 2x. So then we get cosine squared of x minus sine squared of y. Awesome. And you'll notice this is also factorable. It's like the a squared minus b squared term. But anyway, those are our 4 relations, and this is a small lesson over Euler's identity and where you can use it mathematically. And then really quickly, I'll just show you actually, I think that'll be all for this video. I was going to show you maybe where this would be important. So say you were wanting to compute an integral of this term, cosine squared x minus sine squared y, or sorry, this is supposed to be x. Then you would you could try to integrate these two terms in linear terms, or you could just realize that this is just double angle and this simple u sub integral calculation. But anyway, that is all for today. If anyone has any feedback or advice on how I should try to continue any of these videos, educational and AI, let me know, and have a great rest of your day.